Welcome to today's webinar, AWS IoT Real-Time Stream Processing with Lambda. Our presenter today is Vyom Nagrani. Vyom is a Senior Product Manager for AWS Lambda, a compute service that runs your code in response to events and automatically manages the compute resources for you. Lambda helps developers think about applications in a new way by creating simple event handlers that respond to updates from Amazon S3, DynamoDB, Kinesis, SNS, and other services, as well as directly from web and mobile apps. He holds an MBA from the University of Michigan and has previous experience across product management, product marketing, and product engineering. Today with us, we also have AJ Nair, Principal Product Manager, and Brian Liston, Product Manager for Lambda. They will engage with you and answer your questions throughout the presentation while our presenter presents. Vyom, welcome. I now pass the floor to you.
Thanks, Ryan. Hello, everybody, and welcome to today's webinar. My name is Vyom Nagrani, and I'll be your presenter for today. I have with me here Ajay and Brian from the product management team for AWS Lambda to help address your questions over chat throughout the webinar. We'll also do an open Q&A at the end of the webinar if time permits, where I will address the commonly asked questions as part of the webinar presentation. A quick note on the Q&A though, we do welcome all types of questions during this webinar, but the Q&A panel will not be able to address roadmap questions or timelines of upcoming features on the services covered in this webinar. So we do apologize for that in advance. The intention here is to help you understand all of these services discussed in depth. So we have to give priority to addressing the technical questions around building IoT applications using AWS Lambda. We encourage you to post your feature requests or timeline requests to the AWS discussion forums. We actively collect customer feedback and votes from these forums. So please do go over to the forums and let us know what's important for you. With that said, let's jump into the webinar. We'll be breaking the webinar into 3 parts today. First, I will start off by a walkthrough of a reference architecture and code template for how to set up a production-grade IoT stream processing application on AWS using Amazon Kinesis and AWS Lambda. Then we will go a bit deeper into the features and functionality of AWS IoT, a new service by AWS, which can make building such backend applications on AWS very easy. Lastly, we'll go through a quick demo of how to set up an IoT backend application using these 2 services on the AWS console. But first, let's do a quick recap of AWS Lambda. AWS Lambda lets you run code without provisioning or managing servers. You pay only for the compute time that you consume, so there is no charge when your code is not running. With Lambda, you don't have to provision your own instances, since Lambda performs all the operational and administrative activities on your behalf. So things like capacity provisioning, monitoring fleet health, applying security patches to the underlying compute resources, even deploying your code, running a web service front end, monitoring, logging of your code, all of these are taken care of by the Lambda system. Lambda provides easy scaling and high availability to your code without any additional effort on your part. You can set up your code to be automatically triggered from other AWS services, or you can even call it directly from any web, mobile, or IoT application. Lambda is designed to process events within milliseconds of receiving the event, and that kind of makes it easy to execute code in response to events using Lambda, such as changes to an Amazon S3 bucket, an update to a DynamoDB table, or even custom events generated by your applications or even your devices. For example, you can trigger a Lambda function to automatically create a thumbnail when an image is uploaded to Amazon S3, or notifications are sent on a message bus using Amazon SNS, or even processing clickstream data through an Amazon Kinesis stream. Lambda functions can also be invoked directly from external sources, both synchronously and asynchronously. That external source could be a mobile application, it could be a web browser, or it could even be an IoT device, which makes it very easy to build these backend services to perform workloads such as image analysis, document transformation, indexing, and of course stream processing using for IoT devices. Lambda allows users to focus on building these powerful, dynamic, and modular applications in the cloud while not distracting their productivity in undifferentiated heavy lifting of managing infrastructure. Lambda automatically runs your code on high availability compute infrastructure under the hoods and performs all the administration of the underlying compute resources, such as server and OS maintenance, capacity provisioning, automatic scaling happening much faster, code and security patch deployment, monitoring, logging, etc. All you need to do as a developer is to write the code. Now, Lambda supports Node.js, Java, and Python as programming languages today. Our goal is to make Lambda a polyglot platform. That's a platform that supports multiple languages. So when you are getting started with Lambda, there is no new language for you to learn. The main benefit of Lambda for building these IoT backend type applications is that there are no servers to provision or manage. Now, you don't need to plan for capacity. You don't need to worry about going through the server patches, upgrade, software installation, or even like things like being paged when your servers are down. All of these are automatically taken care of. Also, Lambda runs your code only when needed with no unnecessary cost. So with Lambda, you don't need to build out and maintain a fleet of servers and then pay for the time that they sit and wait for jobs to run. Instead, Lambda charges a low fee per request and for the time that your code runs, making it cost effective to build solutions that scale from teeny tiny one request a month to thousands of requests or even millions of requests coming in per month. The last benefit here is sub-second metering. AWS overall has changed the way traditional IT behavior for procurement of infrastructure. Earlier, IT admins used to buy hardware servers and then pay for everything upfront, then get 3 to 5 year commitments for the hardware that they procure, and 8 to 10 year commitments for the data centers that you lease. AWS has changed this to allow customers to pay for infrastructure capacity in chunks of 1 hour. But AWS Lambda takes this to the next level, where you pay in increments of 100 milliseconds. This means that if your API call takes 15.7 seconds to execute, you only pay for those 15.7 seconds. These features or these benefits put together effectively allow you to get an instant 100% utilization on your compute fleet. No more paying for idle, no more being under provisioned for peak or over provisioned for off season. Lambda scales exactly where you want it to scale. So with that, let's see what it takes to build a production grade application for real-time stream processing for IoT workloads. Here's a basic workflow for this setup. The entry point is an Amazon Kinesis stream, which allows you to capture a whole stream of information being sent by different sensors or actuators or devices from your IoT application, from your end consumers, and being able to upload all of that stream of information onto AWS. AWS Lambda then is used to read data and process the data off of the Kinesis stream. And Lambda is automatically triggered through Amazon Kinesis whenever data is available. AWS Lambda uses Amazon DynamoDB as a backend for storing the information and creating file indexes or creating data indexes to read the information whenever required for further processing. So let's look at what a reference architecture would look like for this. This setup demonstrates how to use Lambda in conjunction with the DIY setup that we just talked about to include things like Amazon Kinesis, Amazon DynamoDB, Amazon S3, Amazon CloudWatch, etc. to build a complete serverless system for ingesting and processing sensor data. Let's look at the reference architecture diagram here and break down each of these components to give you an idea of the functionality of this setup. The box labeled number 1 at the bottom is Amazon Kinesis. That's the entry point that we talked about. Devices send events with data to Amazon Kinesis, which provides a large-scale durable storage of all of the events for up to 7 days and allows multiple Lambda functions to process all of these events. Number 2, next to it, is the first Lambda function. This function processes the incoming events and stores the events data in a table in DynamoDB for low latency access. The function also sends values to CloudWatch for simple monitoring of the aggregate metrics. Number 3 on the right is the second Lambda function, which processes the same events as above, but aggregates and stores the incoming events to S3 for raw storage. Box 5 on the further right is this S3 storage for cost-effective, long-term, durable archival of the raw events. Storing data in S3 also makes it easily accessible for analytics processing with Amazon Elastic MapReduce or Amazon Redshift. That's a block 6 at the top. Event data no longer needed to automatically migrate to Amazon Glacier. So things which you can set a certain retention period and create a lifecycle management policy whereby things which you don't access are automatically moved over to Amazon Glacier for long-term archival. Block 6 also represents the analytics portion of this setup, where Amazon EMR runs jobs that read and write data directly to DynamoDB and S3 to analyze the data, generate aggregates, create things like billing reports on the large set of events gathered from the device fleet. Event data from S3 is loaded onto Amazon Redshift to allow interactive exploration and analysis of the data using standard SQL-like queries. The setup also includes a bonus box 4 on the far left. That's a third Lambda function that provides a synchronous interface that devices can call to directly retrieve data from Amazon DynamoDB. For instance, this can be used to retrieve configuration information or historical event data, or storing the state information that the devices may need. We have also open sourced the sample code for all the Lambda functions and the CloudFormation templates for creating these functions and related resources that we talked about in this setup. There's also a simple web page that you can run locally to publish sample events and query the data from DynamoDB. Let me quickly walk through the resources available as part of this code base. The first is the Lambda functions that we talked about in the reference architecture, one for querying the sensor data, the next to persist the data to DynamoDB streams and S3 and CloudWatch metrics. The third one is to process incoming events and archive the raw data. The function roles provide these three functions the right permissions on IAM to execute the read-write or on the related services that they need to talk to. The two event source mappings hook up the second and third Lambda function above to the DynamoDB streams and Kinesis for processing these streams. The codebase also contains the IAM user used by the test web page, the IAM policy to grant permissions to that user, and the access keys to enable this web page to sign API requests. The package provides other resources such as the event stream that we need to create on Kinesis for ingestion of the data, the DynamoDB table for storing the data and the metadata, and the S3 bucket for archival. Lastly, it also holds all the configuration needed to make all of this work, the whole setup work seamlessly. The good thing about this setup is that you don't need to dive into or edit any of this content to get started. This entire system can be deployed in your AWS account using the provided CloudFormation template, and all you need is an S3 bucket. In fact, we have a simple button on the GitHub repo linked here that allows you to deploy this entire stack in your account in US East 1 with just a single click. You can download the testpage.html as part of this package to your local desktop or laptop. Edit the file with the configuration values you get from the CloudFormation script. It will return a lot of the Amazon resource names. So you enter those values into the HTML file and then open that page on your browser. After you launch the test page, you can simulate the submission of sensor data from multiple devices. So you don't even need actual devices to run this template. You can also query the DynamoDB table for historical values of data for a given device. In addition, you can use the test page to query DynamoDB. You can also check the CloudWatch metrics published under a specific namespace in your CloudWatch. This reference architecture sample is licensed under Apache 2.0, so feel free to download it and try it out, and let us know how you like it. So from here, let's look at the AWS IoT service and how the same setup would look like with AWS IoT. AWS IoT is a managed cloud platform that lets connected devices easily and securely interact with cloud applications and other devices. AWS IoT can support billions of devices and trillions of messages and can process and route these messages to various AWS endpoints and other devices reliably and securely. With AWS IoT, your applications can keep track of and communicate with all of your other devices all the time, even when they're not connected. AWS IoT makes it easy to use AWS services like Lambda, Kinesis, S3, Amazon Machine Learning, DynamoDB, etc. to build IoT applications that gather, process, analyze, and present data generated by connected devices without having to manage any of the infrastructure. AWS IoT offers a common set of capabilities that you will likely need, no matter what your IoT scenario is and what application you are targeting. This may range from connecting with the devices to managing the communication network to the security that you want from your application, to collection of devices data from all of the devices, to the intelligence behind your application. AWS IoT offers these capabilities to you so that you can focus on what differentiates your connected devices, the application, and the IoT service that you provide to your end customers. The primary functionality of this service is the connectivity between the devices and the AWS cloud. With AWS IoT, you can communicate with connected devices securely with low latency and low overhead. The communication can scale to as many devices as you want. AWS IoT supports standard communication protocols such as HTTP and MQTT for talking to your devices, and communication is secured through TLS. Secondly, AWS IoT enables processing data sent from these connected devices. So with AWS IoT, you can continuously ingest, filter, transform, route, etc. the data streamed from these connected devices. You can also take actions based on the data and route it to further processing and analytics, and I'll talk of that in a little bit. Finally, a big part of AWS IoT is to make it really easy to create and accelerate application interaction with these connected devices. It serves as an easy interface for applications running in the cloud or on mobile devices to access this data sent from your connected devices, and also send data back and forth between these devices. So let's talk about the benefits, or why this is a good tool for building IoT backends. Now, connected devices such as sensors, actuators, embedded devices, smart appliances, wearable devices, all of these are becoming more proliferant now, and all of these can connect to AWS IoT over HTTPS or secure MQTT. Included in AWS IoT is a device gateway that allows you to allow secure, low latency, low overhead, bidirectional communication between these connected devices and your cloud or your mobile application. And we'll dive into each of these components that I talk about in a little bit. The communication with AWS IoT is secure. The service requires all of its clients, whether it's the connected device or it's the server application or the mobile application of the human users. All of these are required to use strong authentication, such as X.509 certificates, the AWS IAM credentials. You can even do third-party authentication via AWS Cognito. And since all the AWS communication is encrypted, AWS IoT offers a fine-grained authorization to isolate and secure these communication among all authenticated clients. The device gateway supports the pub-sub messaging pattern, which enables a scalable communication platform for one-to-many communication. It is particularly useful for IoT scenarios where billions of devices are expected to communicate frequently with minimal delay. The PubSub involves clients publishing messages on logical communication channels called topics, and the clients subscribing to these topics to receive these messages. The device gateway enables the communication between these publishers and the subscribers. Now, traditionally, organizations had to provision, operate, scale, maintain, and basically operate their whole fleet of servers as device gateways to take advantage of this PubSub communication. But AWS IoT service has eliminated this barrier by providing the AWS device gateway. The AWS IoT service also contains a rules engine, which enables continuous processing of data sent by connected devices. So you can configure rules to filter and transform the data. You can also configure rules to route the data to other AWS services, such as DynamoDB, Lambda, SNS, etc. for now the second stage of processing, storage, or analytics. So we talked about Lambda and we talked about AWS IoT, but the combination of these two services working together is very powerful. AWS IoT can act as the front end or the gateway that interfaces with your device using MQTT as a communication protocol and X.509 certificates for authentication. Lambda can act as a compute backend for your service, managing the compute resources for you and executing your custom logic when needed to respond to these device updates. So with these two services, without managing or setting up any infrastructure, you can build your entire application stack in minutes, and the stack will operate cost effectively at any scale. So let's start diving into the working of the AWS IoT service. And let's take each of the components that we talked about. The device gateway forms the backbone of the communication between the connected devices and the cloud capabilities such as the rest of the AWS IoT service. The device gateway scales automatically with your usage without any operational overhead from you. So it's a automatic scaled part of the service. AWS IoT supports secure communication with the device gateway. You can do things like AWS account level isolation or fine-grained authorization within an AWS account. The IoT device SDK is used to simplify and accelerate the development of code running on your connected devices. So the actual devices itself, such as microcontrollers, sensors, actuators, smart appliances, wearable devices, etc. First, the devices can optimize the memory, power, and network consumption of the underlying resources using the device SDKs. At the same time, the device SDKs also enable a highly secure, low latency, low overhead communication with built-in TLS and MQTT support. The device SDK also accelerates IoT application development by supporting higher level abstractions, such as synchronizing the state of the device with its shadow. I'll talk about that in a sec. And now also communication with the rest of the AWS IoT service. The device SDKs are freely available as open source projects, so anybody can pick them up and start developing. For authentication, the control plane HTTPS requests sent to AWS IoT are authenticated using AWS IAM or AWS Cognito, both of which support the AWS SIGWI4 authentication. If you use the AWS SDK or the AWS CLI, the SIGWI4 authentication is taken care of under the hood, so you don't need to do something explicit there. You just need to log in with your credentials. For data plane operations, basically from the device to the cloud, the HTTPS request can be authenticated using X.509 certificates, and the MQTT messages, for example, sent to AWS IoT are authenticated using these X.509. Then we come to the main part of the IoT service of interest here is the rules engine. The IoT rules engine enables continuous processing of inbound data from devices to the AWS IoT service. So you can configure rules in the rules engine in an intuitive SQL-like syntax to automatically filter and transform inbound data. You can further configure rules to route this data or route selected data from AWS IoT to several other AWS services or even your own third-party services. A thing shadow, sometimes referred to as a device shadow, is a JSON document that is used to store and retrieve the state information for a thing or a device or an app and so on. So the thing shadow maintains a shadow for every device that you have connected to AWS IoT, and then you can use these thing shadows to get and set the state of your device over MQTT or HTTP, regardless of whether the actual device is connected to the internet or not, because the thing shadow is just a virtual entity sitting in the cloud which is always on. And each thing shadow is uniquely identified by its name. And then later, the device SDK automatically manages the synchronization with the shadow. So if the application can set the state in the shadow, and the shadow will automatically sync with the device whenever we have internet connectivity. The last component is the device registry. Now, IoT scenarios can range from a small number of devices to of mission critical devices to a large fleet of devices if you're talking about B2C application. The AWS IoT device registry allows you to organize and track all of these devices, and you can maintain a logical handle in the device registry for every device that is connected to AWS IoT. Each device in the device registry can be uniquely identified and can have metadata associated with it, such as model number, support contact, the certificates associated with it, etc. And you can search for connected devices in the device registry based on this metadata. And then of course, like any other AWS service, you can use the AWS Management Console, the AWS SDKs, the CLI, even the AWS IoT APIs to access the whole AWS IoT service. So let's walk through a little bit deeper into some of the important components that we touched upon in this slide. And the first one I want to talk about is the rules engine. As we said, as we discussed, the rules engine gives your things the ability to interact with AWS services. So rules are analyzed and actions are performed based on the MQTT topic stream. So you can use rules to support tasks such as augment this data or filter the data received from a device. You can even do things like write data received from a device if it matches a certain pattern to an Amazon DynamoDB database. A rule is basically a SQL statement that specifies the pub sub topic to apply on the rule, the data transformation to perform, if any, and the condition under which this rule should be executed. The rule is applied on every message published on the specified topic. The rule definitions use a JSON-based schema, and you can directly edit this JSON, or you can use the rules editor in the AWS Management Console if you prefer. All rules include a SQL statement that consists of a select clause and an optional where clause. The select clause is where you specify what data you want to extract from the entire stream. JSON objects or attributes from the MQTT payload are examples of that. And the where clause allows you to filter these JSON objects that you based on the attributes extracted from the select clause. The system supports a lot of inbuilt functions for string manipulation, math operations, crypto support, timestamping, random number generation, etc., which also allow you to do very complex evaluations, where you can say, I want to filter out data between this and this time, or which has this mathematical parameters. The rules engine also allows many-to-many operations on your device. SQL queries can span the whole fleet of devices in a single query when you need to take actions based on multiple inputs. On the other hand, the pub sub functionality also allows multiple devices to take action based on a single input rule or a single rule match. The second half of the IoT rule is the actions list that it defines. That's the actions to take when this rule is executed. That is, when the incoming messages match the specified rule and the rule is triggered. You can define actions to write data to a DynamoDB database or a Kinesis stream, or you can even invoke a Lambda function. There are a bunch of actions which are directly supported, such as I talked about writing a file to an S3 bucket, writing data to DynamoDB database, publishing a message to SNS, and so on. You can even republish the same message onto another MQTT topic to AWS IoT. But the one of interest to us is invoking the Lambda function. You can also reach to external endpoints like a Slack channel or a Splunk log once you have the data inside the Lambda function, because you own the code of the Lambda function. Before we move on, I want to briefly touch upon the device shadow, because that's another very important thing to think about here. The device shadows enable cloud and mobile applications to easily interact with connected devices registered on AWS IoT. A device shadow in AWS IoT contains properties of a connected device, so you can define and set any of these properties applicable to your use case. The connected device is expected to report the actual values of these properties, which are then stored as the state information in device shadow. And then applications get and update these properties on the device shadow using the RESTful APIs provided by the AWS IoT service, instead of the application directly talking to the end device. The AWS IoT service and the AWS IoT SDKs take care of the synchronization of these property values between the device and the shadow on the service. So you can have applications communicate directly to the connected devices. That is an option. However, we do recommend that we use the device registry and the device shadows, since they offer a richer and more structured development and management experience that lets you focus on the unique value you want to create as part of your application that your end consumer sees, rather than you having to focus on underlying communication and synchronization and fallback mechanisms when the thing is not connected to the internet. So AWS IoT has also partnered with hardware manufacturers to make the device SDK available on several IoT devices, such as embedded OSs, microcontroller platforms, etc. We already have partnerships with leading providers such as Intel, Marvell Semiconductor, Broadcom, Texas Instruments, and many others. And we aim to keep this list growing. We have also partnered with these vendors to build IoT Starter Kits for getting started with AWS IoT. The Starter Kits enable you to move quickly from idea to prototype. These are physical kits which are designed to help accelerate cloud-powered prototype development of these connected devices, and you can connect securely to the AWS IoT service from these platforms. All of these kits include a development microcontroller board, the sensors and actuators, the AWS IoT device SDK, and sample applications to get started, along with the getting started guide, so you can easily find the best fit for your product. So you can prototype your product, prototype your end device using these starter SDKs, and you can then go from production based on those prototypes. You can purchase these kits from Amazon.com. If you already have the hardware board from one of these providers, you can directly download the SDK and the samples from the website and get started in minutes. One special case of the IoT Starter Kit I want to talk about is the AWS IoT Button, which was made available during the AWS IoT Mega Contest participants at reInvent 2015. This is the Hello World entry kit to AWS IoT and is based on the Amazon Dash button, which is a stateless Wi-Fi enabled button. The device has very simple logic embedded into it to store a certificate, connect to Amazon using that certificate, post a simple message to the host, and that's all. No additional setup or code is required to get started. All you need to do is just click a button. Like in this case, it's a physical button. The device very quickly enables users to learn rules, shadows, subscription topics, hooking up to Lambda functions, and writing a whole script using the AWS services. So I have a AWS IoT button with me here, and our demo today will start with this button. So here's the workflow which we'll be going through. When I click this AWS IoT button, it is hooked up to the AWS IoT service, and I have set up a rules engine for every click to be forwarded to a Lambda function. What I'm going to be doing in that Lambda function is the Lambda function will have the permissions and the execution role, and it'll use the policy in the right way to be able to take this rules engine, take the data from the IoT button, and then publish it on an SNS topic. And what I'm going to do is I'm going to subscribe my own email address to this SNS topic. So what will happen then is that every time I click the AWS IoT button, it'll go through the whole flow and I'll get an email in my inbox. So let's see how easy it is to configure this infrastructure on the AWS console. This is the only demo we have for today. So I do recommend that anybody in the audience who has any sort of IoT device can connect to the cloud and follow along with me on the AWS console to create a similar setup from this webinar. If you don't have something, then we are going to have a recorded session of this webinar presented to you and made available. So you can take that as a takeaway from this webinar whenever you're ready to start publishing data to the cloud from your devices. The resources created in this demo would be covered by the free tier of both of these services, so there's no additional cost for you for clicking along with me if that's what you're worried about. The first step is creating the Lambda function. So once you log into the AWS console and select AWS Lambda, if you click Get Started Now or Create a Lambda function, you will get to this screen. We have an approach for creating Lambda functions on the console that what we like to call blueprints. A blueprint is a set of configuration and sample code to quickly get started for integrating with a specific trigger. But here I'm going to bypass this by pressing skip at the bottom and start building my own function. Now for creating the function, Lambda gives you three options. The first is to edit the code in line, which gives you a WYSIWYG type editor where you can directly start typing the code. You can also upload your code along with any additional dependencies or binaries in a zip file directly to the Lambda console. Alternatively, you can upload the zip file to S3 and provide the S3 object details as the source of your Lambda function, which allows you to integrate your custom deployment tools or CI/CD tools directly with AWS Lambda functions. As you can see here, I don't want to do a full walkthrough of the code, but all this code does is it logs the incoming events, it creates an object to publish to SNS, and then it actually publishes that topic to that whole message to a pre-configured topic. It's a simple 15-20 lines of code, but this is just a getting started, so I just want to do a quick walkthrough here. A few additional configuration changes you would need to make in step 2 are listed here. The first configuration is to select the execution role for the Lambda function. This is the permission to allow Lambda to take actions on your behalf by interacting with other AWS services. For example, the sample Lambda function needed, we saw here, needs to write data to CloudWatch logs and also publish to an SNS topic. So the Lambda console provides easy templates for creating these execution roles. You can even select an existing role if you have one. We'll get back to that in a quick sec. But let's first look at the other two settings. That's the memory you want to allocate to your function and the timeout that you want to set. We leave all of these to default values here right now. You can also select VPC access if you need something special here, but we'll also ignore that part of the setup right now because an SNS topic can be a public notification anyway. Let's look at the role creation one a bit more. So here if we select create a new execution role, it automatically directs us to the IAM console on AWS with a pre-populated policy document. You can change the role name here on the AWS IAM console, or you can expand and edit the policy to add more options. Here's a quick look at the policy document. As you can see, the policy does two things. One, it allows Lambda to make changes to CloudWatch logs, and the other is to allow Lambda to interact with SNS. When you click allow on this IAM console page, it will automatically take you back to the Lambda console with this policy created and attached to the Lambda function that you are creating. This last step is the one verification for all the configuration that you have set. If everything looks okay, you can select create the function and you are done setting up the Lambda function. As you can see here, the function was successfully created. What we need to do is run a quick test to make sure the function works perfectly and all our roles are assigned in the right way. You can click on actions to configure the test event object. We'll need to change the object based on what your IoT event schema is. Now, right now, I'm just using a simple payload and a test, a simple JSON notification object here. But now, depending on what the template is for your IoT event coming in, you will need to change this schema for the test object and, of course, your code to match that same schema. But just for this quick test, we'll hit save and test. And you will see that now this function has succeeded and it has logged all of the logs in the CloudWatch logs too, which we provide on the Lambda console for easy access. And if we move over to my inbox, we will also see that I had subscribed to this SNS topic. So you will see that the email that I got that you're having a message from the IoT device, which also shows test message. So from there, let's go into the IoT part of the setup. Now, what you will need to do is activate your kit or your button, and that will be part of the kit that you receive. It will be a simple URL where you can go to activate the button. Activation normally means three things. First, you create a thing on the AWS, or basically the thing shadow on the AWS IoT service. You create a certificate for the device which you're going to be using, and you create a policy to allow this device to publish to the AWS IoT. So when you activate your device, all of these things should be done automatically for you. Then you create the rule that you want to create. Here I'm going to create a custom rule instead of picking from the existing options. And I'm going to create a rule called SNS to Lambda, which creates a SQL query that just says select star from IoT button instead of, it just passes all of the messages through and publishes that to a Lambda function that I select. And from the drop down, you can select the Lambda function that we just created, which is Lambda to SNS. On the AWS console, you will see all of these show up. Now, once you go through this configuration, if you go to the AWS IoT console, you will see all of these available directly on the console. You see the button policy that you created. You see the button shadow which you have created. You also see the certificate that you have set up, and also the rule which you created that goes from IoT to Lambda. So with this, we are ready to go. When I click my IoT button, it will publish a message via MQTT to AWS IoT, which will invoke AWS Lambda, which we have configured to publish to SNS, which I have subscribed myself to. So let's see what that email looks like. So as you can see, this email, the JSON schema is slightly different. It's going to talk about the serial number, what battery is left on the device itself, and here the battery device is the IoT button, and also the click type, because I just did a single click. So while this was a simple demo where I get an email based on clicking a button, the power of this is that the logic is now totally configurable via the AWS IoT rule, and the action is completely configurable via the Lambda function. And you can build very powerful applications using this combination, such as every time my smart weather sensor indicates a temperature of 60 degrees or lower, turn on the heater on my house. Or if my factory liquid flow regulators indicate a buildup of pressure, then automatically shut down that component and page the on-call supervisor. So you can build any of these complex logic applications using the AWS IoT devices and the Lambda functions. The use cases for smart IoT devices is something which I don't really need to talk about, where the smartness in the cloud, because these use cases are in the cloud, are limitless. So in summary, we have three steps for you. Now, first, of course, is to connect your IoT device to the AWS IoT service, or purchase one of the AWS hardware starter kits to get started. With just a few clicks in the management console, you can create the device policy and the rules that enable you to securely and easily connect your device to the cloud to access data, to configure the business logic, or build this functionality for your backend service. We also invite you to create and test your Lambda functions. With AWS Lambda, there are no new languages, tools, or frameworks to learn. Remember, the first 1 million invokes per month are on us, so absolutely feel free to try that out. You can also use the reference architecture we talked about. Now, you need to set up some of the things in your account, like the Kinesis and DynamoDB. But most of the things in that device should also be covered in the free tier for most of these services. And of course, the last point is to select Lambda as the rule action for your AWS IoT device. You can use the sample code and set up instructions that we have provided to quickly create your first IoT device backend application using AWS IoT and AWS Lambda. And then once you have everything set up, all you need to do is just send your stream of devices, because AWS IoT front end will scale from one device to millions of devices very, very quickly without you having to change anything on the setup. And there you have your streaming application set up using AWS IoT and AWS Lambda, just 2 services as compared to the whole reference architecture we talked about. So that's all I had from my end from the presentation. I'll hand it back to Ryan. We'll take a couple of minutes of quick break after that, and then we can address some of the open questions from the Q&A forums. So back to you, Ryan. Thank you, everybody.
Okay, thanks a lot. And at this point, please take a few minutes to respond to the 3 polls on the left-hand side of your screen. Continue submitting your questions, and we will have about 13 minutes for live Q&A at this point. Thank you.
Okay, welcome back for the Q&A. I'll start talking to some of the questions which were commonly asked during the presentation. One I hear from James is, we keep hearing that you don't need to worry about capacity with Lambda, but AWS does a account level limit on concurrency. What strategy should we use to make sure Lambda doesn't drop events with high concurrency workloads? So, want to talk about the concurrency limits here a little bit. AWS Lambda offers a safety throttle on the functions when you are getting started. So what we do is that behind the scenes, when you start with AWS Lambda, you are limited to 100 concurrent requests. So at a given point in time, the system will not fan out to more than 100 parallel copies. But this is only a safety limit. This is only to allow you, as you are getting started, to be protected from runaway functions or recursive loops, or accidentally hooking up a production stream or a production traffic to a test function. This is a completely configurable limit. It's a soft limit. You can go into the system, request a limit increase. And we have customers who are doing now tens of thousands of concurrent copies today. So just wanted to let you know that this is not a hard limit. Now you can have Lambda to handle a lot of the things that happen at these concurrent high traffic workloads. So that's one part of the picture, that you definitely can get this limit increase. So it's not something which is a hard limit. The second part of the workload is that what happens now in case there is a huge spike of data. which I had configured my system to go to 5,000 concurrent, for example, because that's the average traffic I expect. What happens for that 1 second when the power went out, and because everything power comes back on together, a million devices are trying to communicate to the cloud and sending new updates at the same second. Well, in that case, the AWS IoT service behind the scenes communicates via asynchronous invokes to Lambda behind the scenes. And what this means is that Lambda works as a asynchronous worker, which means any event which is coming from AWS IoT onto Lambda will first be queued inside of Lambda, and then Lambda processes off of that queue. And this allows you to send in a huge spike of traffic to AWS IoT or to Lambda, and then Lambda will not drop any of those events. It'll absorb that whole burst of data that comes in, and then it'll just process off of that queue at your concurrent limit. If your concurrent limit is 5,000 and every function takes a second to execute, if you send in a burst of 500,000 requests coming into Lambda, all that means is that everything will get queued, and the last message to come in will get processed 100 seconds later. None of the data is dropped, so that definitely is another way of using AWS IoT and Lambda, because you don't have to worry about your system being scaled all the way to the level. You can still use 5,000 as the safety limit for your functions, and then you simply use this burst mode to be able to process the remaining events. I see a couple of questions around what does Kinesis do in this picture? Why not stream the data directly into Lambda from Raj? Or similar question from Tarun is it really required to use a Kinesis stream to process these events, or can IoT invoke Lambda functions directly? So definitely yes, you can invoke the Lambda function directly. You can have the device. If the device is configured, you can use either the AWS IoT service, or you can use Kinesis, or you can invoke Lambda directly. So you have a couple of options, and depending on what you want, what functionality you want, you can pick one of those options. If you are invoking the Lambda function directly, remember that Lambda takes SIGWI 4 credentials for users in your account. So what you would need to do is that the device would now need to have the AWS SDK, and it would need to have a user role to invoke the function. That normally is okay if you're going in a mode where you're going to create a separate user and then have only those user credentials embedded onto the device. But if your device is not, if it's a very low-end application device, it's like a wearable technology, or it's something very lightweight, where you don't want to have the whole AWS SDK embedded onto your device, then you can simply have the device SDK and then have that device push to AWS IoT instead of having the whole SDK embedded onto it. Another option actually is for your device to make a RESTful, like a REST HTTP call, and then you can back your Lambda function with Amazon API Gateway. So that way the device doesn't need any sort of SDKs at all. All it's making is a HTTPS post request for every time it needs to synchronize the data. But then the difficulty there is going to be talking back to the device. That's going to be a bit of a problem, which is why you might want to go with the device SDK. The benefit that Kinesis adds in here is Kinesis makes it very easy to manage and operate a stream on top of AWS. So Kinesis has this construct called shards, where you can create multiple shards based on your partition key, so that you can quickly add more and more data in a managed stream sort of environment going into AWS. And Kinesis offers a lot of additional functionality, such as long-term storage. The data that you write to Kinesis is persisted for 7 days. Sometimes ordering is very important. If a device registers 30 degrees at one point and then 35 degrees later, it's important for you to know if the temperature went from 30 to 35 or it went from 35 to 30. So the order of the invoke is also important, and Kinesis also does that for you. Kinesis manages ordered processing, which means you would get the data at the output in the same order in which you set it at the input, and Lambda continues that whole ordered processing framework, so that you get the data in the same and you can process the data in the same order. The third benefit that Kinesis adds when invoking Lambda functions is batching of data. Now, oftentimes you don't want to invoke a Lambda function for every device update. Now you're trying to do some sort of aggregation, or you're trying to pull some sort of metrics anyway. So you want more of an aggregation. With Kinesis, you can set up a batch size of up to 10,000 records. So as you are streaming in lots of data into Kinesis, you want to invoke Lambda function once only every 10,000 records to do that aggregation job for you. And that's another functionality that Kinesis can add to be able to invoke a Lambda function for every batch of data or every batch of events instead of directly. We have a question from Tim. Can Lambda include a logic that will self-trigger in the event that the message is not arrived? That is a fail-safe system. So for what I understand is that you are looking for some sort of way in which you can have the Lambda function get invoked every few minutes anyway, just to check if there was any data. Now, if the data is not there, you want to do a periodic cleanup job anyway. So Lambda now allows you to be invoked off of a schedule. So with CloudWatch events, there's a new construct called schedules. So you can have the schedule event invoke the Lambda function, and you can create this directly from the Lambda console as well, where you can have a Lambda function be invoked every 5 minutes, and that Lambda function will wake up and it can do all of this cleanup job or the self-trigger mechanism just to wake up and check if the events were arrived on time or not, if just to as a backup check to see that the system is still executing. You can actually start building things like your monitoring systems or canaries on the system. You can also do that the Lambda function wakes up every 5 minutes. If it hasn't seen any invokes, it can go and just poll the devices just to make sure that the devices are still connected. So you can do all of that sort of periodic type of batch jobs on top of AWS and Lambda. One last question I'll talk about is that can you connect the Alexa voice service to AWS IoT? So with that one, I'd rather say that the Alexa voice service right now integrates directly with the Lambda function. So you can have you can include the Alexa SDK inside your applications, and then you can build these voice-based applications that can trigger a Lambda function. So every time you go and start the application, instead of saying Alexa, what time is it, you can say Alexa invoke Lambda function X, and then it'll go in the back end, and you can actually create mnemonics around this, where you can change what you say, and then every time Alexa gets called, it will directly invoke the Lambda function behind the scenes. And here you want to use this direct integration instead of going through an asynchronous mechanism, because here there is an end user who is actually waiting to hear what Alexa responds back. So you can't go through the AWS IoT because that's asynchronous processing, and you won't be able to get the message back to the device through the same API call. With the Alexa voice service integration directly with Lambda, it gets called synchronously. So the device will call the Alexa servers, which will connect to the Lambda function. Lambda will process that request. It gets the whole voice text as a transcript inside the message inside the Lambda function. It can process that what the user has said. It can find the next logical steps because your whole logic lies inside of Lambda, and respond to the Alexa device straight on that same API call. So Alexa can respond back to the user who asked the question. So we definitely think that that's a very interesting use case in IoT space, but the best way of using it is to go directly to Lambda. Okay, with that said, we are at the top of the hour, so I'd like to respect everybody's time. Thank you very much for everybody who attended this webinar. I hope this was useful to you. Thank you. Bye-bye.
I'd like to extend a special thank you to our presenter Vyom for his time and a great presentation, and also to AJ and Brian for answering the audience's questions. If you have any comments on our previous and upcoming webinars or suggestions on the topics you wish AWS may cover in future webinars, please feel free to email aws-webcasts@amazon.com. Your feedback will help us improve our webinar programming. Thank you to our audience for taking the time to join us today, and enjoy the rest of your day.